Hello, my name's Nabil Khan, and today I'll be presenting a machine learning project that I'm pretty excited to share with you. We'll be predicting chemotherapy-induced cardiotoxicity using both radiology imaging as well as medication data. Chemotherapy is essential for treating cancer, but it often comes with severe side effects, one of which is cardiotoxicity or damage to the heart. This cardiotoxicity can lead to heart failure or even other cardiac complications. And while we know that certain chemotherapy drugs, such as anthracyclines or trastuzumabs, are more likely to cause this, it's still difficult to predict which specific patients will be affected. My project aims to solve this problem by combining radiology imaging data and detailed medication records to predict the risk of cardiotoxicity on an individual basis using machine learning. Now, when it comes to considering the potential of this project, we first need to ensure that we've selected the right opportunity for applying machine learning. To do this, we focus on three key questions. Is there a problem worth solving? Can machine learning help solve this problem? And finally, does solving the problem matter to someone? Well, there is a clear problem. It's chemotherapy-induced cardiotoxicity, which is a significant health risk and lacks reliable prediction tools. Machine learning can help solve this problem. It's well suited for analyzing the complex data sets that are required to make accurate predictions. And solving the problem does matter, both to patients as well as healthcare providers. They stand to benefit from a solution that can reduce the risks and costs associated with chemotherapy-related heart damage. Given these factors, this project is an ideal candidate for applying machine learning to create a meaningful, impactful solution. Following the opportunity evaluation, we'll now turn to how we structure the development of our solution using a proven methodology. In data mining and machine learning projects, it's essential to have a clear and systematic process that ensures that we achieve meaningful, actionable results. This is where the CRISP-DM framework comes into play. CRISP-DM stands for Cross-Industry Standard Process for Data Mining, DM. It's the leading methodology used for guiding data-driven projects from conception to deployment. Let's briefly explore its history and why it's become the go-to standard in machine learning and data mining, followed by a 6-phase step-by-step explanation that shows why it's so effective. The Cross-Industry Standard Process for Data Mining, CRISP-DM, was developed in the late 1990s by a consortium led by Daimler AG, SPSS, and NCR. They did this to provide a structured approach for data mining projects. It was specifically designed to be industry agnostic and has since become one of the most widely used methodologies for machine learning and data mining projects. It's mainly valued for its both flexibility and comprehensiveness. So CRISP-DM is used when organizations need a reliable, standardized framework for developing machine learning models or data mining solutions. It ensures that projects follow a structured process. Now let's jump into the 6 phases that comprise CRISP-DM. We start with understanding the business. We define the project's objectives and requirements from a business perspective. We then move on to understanding the data. So we collect and explore the data to improve quality issues, and we also gain initial insights in the second phase. Next up, there's data preparation. Clean, format, transforming the data, making sure it's suitable for the next step, modeling. Now in modeling, we select and apply appropriate machine learning algorithms to the prepared data. We then move on to evaluation, which is assessing the model's performance and ensuring that it meets the business objectives. And lastly, deployment, implementing the model in a real-world environment to provide actionable results. Let's go through each phase briefly and see how they relate to our cardiotoxicity prediction process. The first phase is business understanding. This is one of the most crucial phases because it ensures that we're solving a problem that actually matters. So here, We define the business objectives, clarify the problem, and outline what success looks like from both a business and technical perspective. For our project, the business objective is pretty clear. It's to predict whether cancer patients undergoing chemotherapy are at risk of developing cardiotoxicity. So, this is crucial. It allows clinicians to intervene early, they can potentially adjust chemotherapy doses, perhaps they can prescribe cardioprotective agents, or simply implement more frequent cardiac monitoring. Now, from a data mining objective, from the technical standpoint, we'd be looking to build a machine learning model that predicts the likelihood of cardiotoxicity by integrating radiology imaging data and chemotherapy medication records. In this case, we're developing a binary classification model, meaning the outcome is going to be binary, either yes to cardiotoxicity or no. Success in the business sense means reducing the number of adverse cardiac events in cancer patients, which can directly improve patient outcome and reduce healthcare costs. Now, technical success, like success from the technical perspective, it will be defined by the performance of our machine learning model, where key metrics such as accuracy, precision, recall, and AUC will indicate how well our model performs in identifying high-risk patients. The next phase is understanding the data, which involves familiarizing ourselves with the data that will be used in the project. This phase is about exploratory data analysis and is essential to ensure that we know what data we're actually working with, how that data is structured, and if the data is even complete. Now, for this project, the data we will be working with are two key data sets. We have the MIMIC-III clinical database, as well as the MIMIC-CXR database. These databases provide access to detailed patient records, including chemotherapy medication information, cardiac-related lab results, as well as chest radiographs, also known as X-ray images. Now, during this phase, we'll perform data exploration to understand what variables are available and identify any initial relationships in the data. We also assess the quality of the data by checking for missing values, inconsistencies, or outliers that might need addressing during the data preparation phase. For example, we may explore whether certain drugs like anthracyclines correlate with elevated cardiac biomarkers or maybe abnormalities in imaging reports. If we find patterns during this phase, it'll give us an early idea of what features may be important in the modeling phase. Now, after understanding the data, we move on to preparing it, which is often the most time-consuming part of any machine learning project. In this phase, we clean the data, handle missing values, create derived features, and prepare it for modeling. In this project, data preparation involves several key steps. First, we'll need to extract structured data like medication doses, lab results, demographic information, all from the MIMIC-III database. Next, we'll have to apply NLP, which is natural language processing techniques, to process unstructured data such as radiology reports. These reports often contain free text descriptions of imaging findings, so we use tokenization to break sentences into individual words and named entity recognition, known as NER. This will identify key clinical terms like reduced ejection fraction or other similar terms that may indicate early signs of cardiotoxicity. We'll also create derived features from this data, such as cumulative chemotherapy dosages of heart-related biomarkers like BNP, which is an indicator of heart stress. At this stage, we must also normalize or scale the data. For example, imaging features extracted from radiology reports may have different units compared to medication doses. Machine learning models can perform better when input data is on a consistent scale, which is why feature scaling, typically used during standardization and normalization, is applied. Next is the modeling phase, where the real magic of machine learning truly happens. In this phase, we select appropriate machine learning algorithms, train our models, and fine-tune them to maximize performance. For our cardiotoxicity prediction model, we're dealing with a binary classification problem, which means our model will predict whether a patient will experience cardiotoxicity or not. Some algorithms we could use include logistic regression, which is used for binary outcomes, or gradient boosting algorithms such as XGBoost. Each algorithm has its strengths. Logical regression is simple and interpretable, while random forest and XGBoost can capture complex interactions between variables, making them more accurate but potentially harder to interpret. Given that we're working with medical data, interpretability is key, so we may lean towards models that are both powerful as well as explainable. Additionally, during the modeling phase, we'll use cross-validation, specifically k-fold cross-validation, to ensure that our model generalizes well to unseen data. Cross-validation involves splitting the data into multiple folds and then training the model on a subset while validating it on the remaining data. This helps prevent overfitting, which occurs when a model performs well on training data but poorly on new unseen data. Once we've trained the model, we move on to the evaluation phase. Here we test the model's performance using a holdout dataset that was not used during training. This is where we assess key performance metrics such as accuracy, which measures the proportion of correct predictions, and precision and recall, which help evaluate how well the model identifies patients at high risk of cardiotoxicity. One particularly important metric for this kind of project is the ROC-AUC score. This is short for Receiver Operating Characteristic Area Under the Curve. The AUC represents the model's ability to distinguish between patients who will develop cardiotoxicity and those who won't across all classification thresholds. A perfect model would have an AUC of 1, while a random guess would result in an AUC of 0.5. In healthcare, we aim for high precision in high-risk predictions because the stakes, such as unnecessary treatment changes or misdiagnosis, are extremely high. Finally, the last phase is deployment. This phase involves integrating the model into clinical practice. Deployment in a healthcare setting requires rigorous validation and compliance with regulations such as HIPAA to ensure patient privacy is maintained. At this stage, we would collaborate with clinicians to embed the model into their workflow. For example, the model could be deployed as part of a clinical decision support system, also known as CDSS, where physicians input patient data and the system returns a cardiotoxicity risk score. This would allow doctors to adjust chemotherapy plans based on the patient's predicted risk. Additionally, continuous monitoring is essential post-deployment to ensure that the model remains effective and that the treatment protocols and patient populations evolve. As I mentioned, my solution uses a supervised machine learning model to predict chemotherapy-induced cardiotoxicity. The validation process will follow a series of iterative experiments, starting with data exploration and feature engineering and continuing through the model training and performance evaluation. We'll validate the model's effectiveness through techniques such as k-fold cross-validation to ensure robustness, and I'll also work with clinicians to gather feedback on how the model performs in real-world scenarios. This will allow us to fine-tune the solution and ensure that it delivers actionable insights in clinical practice. Now, let's dive into the machine learning system design of our cardiotoxicity prediction model. Designing a robust ML system involves several critical decisions, and I'll walk you through the 3 most important considerations. We'll be deciding to use a cloud-based or edge-based system, choosing between offline and online learning, and determining whether to deliver predictions in batch or online. These decisions impact the architecture and performance of the entire system. Starting off with cloud-based versus edge-based systems. The first key decision is whether to use a cloud-based or edge-based system. In this case, a cloud-based system is the clear choice, and here's why. The dataset we're working with is large and complex, incorporating radiology imaging, medication histories, and clinical data. Processing such data requires significant computational power, which cloud platforms like AWS, Google Cloud, or Microsoft Azure can easily provide. In a cloud-based system, we can easily scale our resources depending on the size of the data and the computational requirements for the model. Additionally, cloud systems are ideal when we need to access multiple large datasets, as we do with MIMIC-III and MIMIC-CXR databases. These databases are already housed on servers, making it efficient to process and store data in the cloud. Contrast this with edge-based systems, which run on local devices such as sensors or mobile phones. While edge systems offer low latency predictions by processing the data locally, they wouldn't be practical here. The large amount of imaging data and the complexity of the model require the power and flexibility of the cloud, rather than a small resource-constrained device. Moreover, the model doesn't need to deliver predictions in environments where internet connectivity is an issue. Our target users, such as clinicians in hospitals or cancer centers, will always have internet access, further supporting a cloud-based solution. The second most important decision is whether to use offline or online learning for training the model. In offline learning, the model is trained at fixed intervals using a batch of historical data, while in online learning, the model updates itself continuously as new data arrives. For this project, we'll be using offline learning. This choice is appropriate because patient data, such as medication records, radiology images, they don't change minute by minute, like in some real-world or real-time systems. Instead, we can retain the model at regular intervals, perhaps monthly or quarterly, to incorporate the most up-to-date data from clinical trials or new patient outcomes. Offline learning is advantageous here because it allows for us to perform batch updates and fine-tune the model periodically without needing constant real-time adjustments. In contrast, online learning is better suited for situations where the data is continuously streaming in and where the model must adapt instantly, such as in financial markets or, for example, recommendation systems. For our use case, predicting cardiotoxicity, patients aren't receiving constant updates to their records, so it wouldn't justify using an online model. By retaining the model offline at scheduled intervals will ensure that it remains up to date without the computational overhead of constant retraining. So finally, we need to decide whether we'll generate batch predictions or online predictions. Batch predictions will be the best choice for this project. With batch predictions, we can generate predictions for groups of patients at once, likely during specific times when new clinical data is reviewed. So for example, a hospital may want to assess cardiotoxicity risk for all new cancer patients admitted in the past week. We could run the model on that batch of patients, generating predictions all in one go. This approach contrasts with online predictions, where each prediction is generated immediately when new data comes in. While online predictions are useful in real-time systems, they aren't necessary for this project. Cardiotoxicity doesn't develop within seconds or minutes of chemotherapy administration. It happens over time. As such, the immediate, on-demand prediction capability of online predictions isn't required. Batch predictions provide a more efficient, scalable approach for handling large groups of patients while allowing us to optimize the system's performance. Given these design choices, our technology stack will include cloud infrastructure, so we'll use cloud services like AWS or Google Cloud to handle the computational needs for training and generating predictions. The cloud also provides the necessary storage for large datasets like MIMIC-III or MIMIC-CXR. It involves data processing pipelines, so we'll set up pipelines to pre-process the radiology imaging data and the clinical data to include NLP, natural language processing, for the radiology reports, ensuring that the data is both clean and ready for the next phase, which is modeling. We have model training and batch predictions, so the model will be trained offline at regular intervals. We'll be using powerful cloud GPUs or even TPUs. Predictions will be delivered in batches when new patient groups are evaluated. In terms of deployment, the predictions will be integrated into a clinical decision support system, CDSS, where clinicians can input patient data and receive cardiotoxicity risk assessments. This cloud-based system will ensure that predictions are available to clinicians through a user-friendly interface. By considering these three key system design choices, cloud-based infrastructure, offline learning, and batch predictions, we ensure that the model is both efficient and scalable, while also meeting the needs of clinicians who require accurate, timely predictions for their patients. This structured approach not only optimizes the performance of the model, but it also ensures that it integrates seamlessly into clinical workflows, improving the patient outcome by providing precise, data-driven insights. Now let's talk risks. Deploying machine learning models in healthcare comes with some inherent risks. One concern is data drift. This happens when the distribution of input data changes over time, which could degrade model performance. For example, new chemotherapy protocols or new drugs might alter how the data looks, leading to concept drift. To combat this, I'll implement continuous monitoring of the model's performance and regularly retrain the model with new data. Another risk is training serving skew, which occurs when the data used in production doesn't match the data the model was trained on. This can lead to incorrect predictions, so I'll ensure that the same data processing steps are applied in both the training and production environments. In conclusion, this project presents a unique opportunity to combine machine learning with radiology and pharmacy data to solve a pressing problem in oncology. By predicting chemotherapy-induced cardiotoxicity, we can improve patient outcomes, optimize treatment plans, and reduce the healthcare burden of managing heart-related side effects. Thank you for your time.